Hello everyone, I'm going to present our recent work, Device-Independent Randomness Expansion with the Entangled Photons. This work is a collaboration among several institutions. The experiments were performed at NIST-Boulder, led by Crystal. The high-efficient detectors used were developed by Seoul's group. The quantum random number generators used are from Morgan's group. I worked with Mohammad, Honghao, Mani on theory side of this work. First, let me briefly introduce randomness. In order to obtain a random number, we use a device called a random number generator. The output of the device is a random number if the output has the following properties. The first one is the output is not predictable in advance. When we run the extractor, we do not know the value of the output in advance. The second is the output is uniformly distributed so that each possible value of the output will happen with the same probability. The last property is that for several applications, such as cryptography, we want to make sure only the user of the device knows the value of the outputs. So in that case, the random number is private. Randomness has many applications from real life to scientific research. Quantum mechanics provide multiple ways for generating randomness. Here, I just focus a special way, device-independent randomness generation. In this case, we do not need to trust the quantum device. So we model each device by a black box. Suppose there are two local parties, Alice and Bob. Each one has a black box. At each trial, we can provide a uniform bits to each black box. After the process inside, we can read out the outputs A and B. By repeating this process multiple times, we can estimate the distribution of the output given the input. Then we can test a Bell inequality. If we see a Bell inequality violation, then we can tell local realism is not compatible with experimental results. In other words, the outputs are not deterministic functions of the inputs and any other set information, such as local hidden variables. Hence, the outputs must contain intrinsic randomness. That's the main idea. Because we do not trust how quantum device works, so we call this device-independent randomness generation. Up to now, there are several demonstrations of device-independent randomness generation. Here I list all published works. If you compare the amount of output randomness with the amount of input randomness, you can see there is no net random bits from these experiments. Hence, these experiments didn't achieve randomness expansion. The main obstacle is that all these demonstrations use the CHSH Bell test configuration. So at each trial, we provide two uniform bits, and we read out only two binary outputs. As you know, two binary outputs contains at most 2 bits of randomness. Hence, it is impossible to achieve randomness expansion. And to overcome this obstacle, people have studied spot checking protocol. According to this protocol, there is a trusted third party which coordinates Alice and Bob to choose when a trial is a spot checking trial. If a trial is a spot checking trial, Alice and Bob will perform the standard Bell test. If not, Alice and Bob just use fixed inputs. Since a trial is a spot checking trial with a small probability, in this way we can reduce the input randomness consumed. At the same time, if we make assumption like the untrusted devices do not know in advance when a trial is a spot checking trial, then we can certify randomness produced by every trial. Hence, randomness expansion is possible. The weakness point of this protocol is that for spot checkings, Alice and Bob we need to use non-uniform bits with a specific bias. However, in practice, it is not easy to access a source of non-uniform bits with a specific bias. To avoid using non-uniform bits, we just developed a protocol called blockwise spot checking protocol. According to our protocol, we can group experimental trials into a sequence of blocks. Each block has a random number of trials. That is, the block length is random. Specifically, we use key uniform bits to choose the block length, so each block has at most 2 key trials. We fix the last trial in a block as the spot checking trial, where Alice and Bob perform the standard bell test. For the other trials in a block, Alice and Bob just use fixed inputs. Similar to the usual spot checking protocol, we can make assumptions like the untrusted devices can't learn in advance when a block will end. Then we can certify randomness produced by every trial in a block. At the same time, you can see each block costs k bits for block length determination and 2 bits for setting choices. Hence, it's possible to achieve randomness expansion. Compared with the usual spot checking protocol, our protocol does not consume any non-uniform bits. Next, let me briefly describe our experimental implementation of the protocol. We use a loophole-free bell test configuration. In this configuration, Alice and Bob are far away from each other, so that Alice's measurement outcome is space-like separated from Bob's setting choice in the spot checking trial. Hence, we can close the locality loophole for spot checking trials. Also, Alice and Bob perform measurements with high efficient detectors so that we can close the detection loophole. The detectors were developed by Sewu's group. For spot checking trials, the setting choices of Alice and Bob are chosen by quantum random number generators, which developed by Morgan's group. The entangled states are emitted from the source station. So next, let's look closer at the source station. The source station has 2 parts. One is for generating entangled photon pairs. This part is not trusted. The other part is a trusted third-party spots. Spots use 17 random bits to choose block lengths. These random bits are from NIST randomness beacon. We use 17 random bits according to our security analysis, which I will explain later. On the experimental side, per second, we can generate about 10 million trials. Over 2 weeks, we collected enough data for expansion analysis. When we collected the data, we group data into a series of cycles. Each cycle can up to 1 hour. During a cycle, we monitor the change of experimental parameters, such as detector efficiency and state visibility. If we see an obvious change, we will stop the current cycle and do some calibration and then start a new cycle. In this way, we can track experimental drifts so that it will help our security analysis, as you will see later. So next, I will briefly introduce our analysis method. We use probability estimation to certify randomness. According to this method, we can certify a lower bound on the smooth main entropy. The main results is summarized as this theorem. To obtain these results, we consider the following situation. We consider an experiment which consists a sequence of trials. At each trial, we provide some input Z and get some output C. Over the experiments, the devices used may be correlated with adversary. Particularly, we consider the classical set information of adversary. After the experiments, we can describe the states by the joint distribution of experimental results and the adversaries set information. We call all the possible joint distributions the model of the experiments. Also, during the experiments at each trial, we ensure macro-routine condition is satisfied. That is, the future input is independent of past outputs given the current set information. In our experiments, this condition is satisfied because at each trial, the input distribution is fixed and precisely known. Similarly, for a trial, we can describe it by a model, and then we can construct a function called a probability estimation factor. Later, I will tell you the details of this step. Once we have PEFs, we can see the product of the PEFs over all observed trials, and then check whether the product value is larger than some threshold. If it is, so our experiments succeed, and then we can certify the amount of randomness. Next, let's see how do we describe a trial. The model of a trial includes all possible distributions of trial results. According to quantum mechanics, all the possible distributions form a convex set. However, this convex set has an infinite number of extreme points. This is not good for implementing our method. Instead, we use a superset of this quantum set. The superset is a convex polytope with a finite number of extreme points. Specifically, we consider all the possible distributions satisfy the following two conditions. The first one is the conditional distribution of output satisfies no signaling and sequence bonds. As well known, all quantum distributions satisfy both constraints. The second condition is that the input distribution is fixed according to the protocol. In our blockwise spot checking protocol, the input distribution depends on the position of a trial in a block. So once we know how to describe a trial, we can construct a function called a PEF. In order to define this function, we need a free parameter beta. Then, given arbitrary distribution in the model, we put a constraint on PEF. The constraints read as follows. The product of the PEF and the power of the conditional probability on average is less than or equal to 1. The main idea behind it is that once we have such a function, if this function PEF takes a large value, we know the conditional probability will take a small value. Hence, we can certify randomness. For the blockwise spot checking case, for different trials in a block, the models are different, so we will use different PEFs. In general, we can formulate the construction of PEFs as numerical optimization problem. I will skip the details later, but the main idea is that before the experiments, we can choose PEFs and the power beta such that the amount of randomness certified on average is as large as possible. Similarly, before each trial, we can adapt PEF to be used for a trial by doing a similar optimization. After certifying the amount of randomness, we can extract them by running some extractor. The extractor is a classical algorithm which takes inputs the experimental results as well as a sequence of seed bits in order to generate a sort sequence of uniform bits. Specifically, we consider the traversing extractor. In our demonstration, we didn't run traversing extractor because it is very expensive to run this extractor. However, when we evaluate whether randomness expansion is impossible, we compare the total amount of output bits with the total amount of input bits, including the number of seed bits consumed when running the extractor. The amount of output bits is determined by the amount of randomness certified by our method, as well as the extractor used. Another point is that the output bits are not perfectly uniform. There is an error, so it describes the difference, the distance between the output bits and the ideal uniform bits. The error is contributed by two parts. One is from running the extractor, the other is from certifying randomness. Next, I will present our protocol design and data analysis. There are two major parts. The first part is before the data analysis. We need to fix several parameters, including block lengths. Then the second part is just run the analysis using the parameters fixed and see whether we can achieve randomness expansion. For the first part, we use the calibration data obtained before our experiments and also the commissioning data. The commissioning data is chosen to be the first 16 cycles. For the second part, we use all the remaining data. Specifically, we have about 56 million blocks for expansion analysis. Now let's see the first part. Before the experiments, we need to determine the block lengths. For this purpose, we formulate an optimization problem. It is not hard to see the amount or the number of trails required depends on the block length. Hence, we can try to choose a proper block length in order to minimize the number of trails required for expansion. Accordingly, we choose the block length to be 2 to 17. I will skip the details for this step. Due to this block length, so each block consumes 17 bits for block length determination and 2 bits for setting the choices. At the same time, we estimate each block can produce about 32 random bits. Hence, we can achieve randomness expansion. Also, before the data analysis, we need to fix several other parameters, such as soundness error, smoothness error, PF power beta, success threshold, and also the amount of seed bits used. For this, we just first fix the soundness error according to the 5 sigma confidence criterion. Then, given the soundness error and the amount, the number of blocks available for expansion analysis, we can formulate an optimization problem in order to find the optimal values for beta and smoothness error. The optimization is for maximizing the amount of randomness certified. After that, we can fix the corresponding success threshold and then determine the amount of seed bits used and also the amount of random bits extracted. I will skip the details of this procedure. According to this procedure, when success, we can generate about 1.1 billion random bits by consuming about 1.06 random bits. Hence, we can achieve randomness expansion. Specifically, we expect the expansion ratio will be about 1.1. Before the data analysis, we also need to fix how do we construct PEFs. Since we observed the experimental results drift from cycle to cycle, we decided to update PEFs before each cycle. For this purpose, we use the calibration data collected at the beginning of each cycle. We studied the performance of this updating by this calibration trials. We saw 2 minutes calibration trials is sufficient for this purpose. Next, let me present our main results. Our main results can be summarized into this plot. Here you can see the amount of output random bits certified increases with the number of blocks analyzed. At some point, the amount of output bits surpasses the amount of input bits. At a later point, about 91 hours, our success threshold is satisfied. Hence, our protocol succeeds. We can stop analysis at this point because our construction of PEFs is adaptive. Then we estimate the expansion ratio is about 1.24, which is higher than the expected one before running the analysis because we stop the analysis at an early point, so less amount of input randomness is used. These experiments last about 110 hours. However, the total amount of random bits generated is more than that generated by NIST randomness beacon in the last 3 years. Hence, this achievement is amazing. In the end, I like to briefly mention two other two related works. Besides our work, there are two independent works also demonstrate a device-independent randomness expansion. In contrast with us, they use the Euro spot checking protocol. So this experiment requires non-uniform bits with a specific bias as well as uniform bits as inputs. Also, in contrast with us, their security analysis is against quantum set information. To achieve this goal, one work uses entropy accumulation. The other work uses quantum probability estimation. On the experimental side, their system detection efficiency is about 82%. By comparing their performance with our results, we can see by increasing the detection efficiency by a few percent, the performance of randomness expansion will increase by a lot. With this, I would like to conclude my talk. We devised a block-wise spot checking protocol for randomness expansion. We also demonstrated this randomness expansion with a loophole-free biotest configuration. In the future, we would like to improve our system efficiency. These improvements will bring several benefits for us. The first one is we can reduce the time cost for randomness expansion. The second one is we can upgrade the security analysis. With a higher detection efficiency, we can run an effective optimization problem to upgrade PEFs to quantum estimation factors so that we can achieve analysis against quantum set information. In addition, with a higher detector efficiency, we can run traverse extractor. On the theory side, we would like to study expansion without a trusted third party. We also would like to see the performance of other randomness expansion protocols such as cross-fading. By the way, I would like to mention our current security analysis assume the input random bits are perfect. However, in practice, there are some biases in these input bits. So in the future, we would like to study the effects or imperfections of input bits for expansion analysis. Thank you very much for your attention. And if you have any questions, feel free to ask me over the online conference or email me later. Thank you. Bye.